take a look at this dice.asm program we've been working on here. Let's actually tackle the random number generator. Make this random number generator a little better. This fundamentally gets a random number. I think we want to, let's change the comments to figure out exactly what this is doing rather than just saying get next random number. That'll help us visualize what it's doing, and then we can come up with maybe a better algorithm. Like, at minimum, this should probably have an addition so that it's not strictly even odd. Ideally, we'd kind of like to grab the value from the high word, right? So let's go back and look at how multiply works. So multiply is going to multiply the source by AX and store it into DXAX. And it can be a memory location, 16 bits, which is what we're using. And so we're going to load AX with the number we want to multiply by. We're going to multiply that by the seed. Interestingly, DX... Oh, it doesn't matter what DX has. So we would get FEE9 hex, which if we look up let's do a little search here. If we look at list of primes, Wikipedia has a fine article that's a list of primes. Bring up SpeedCrunch. What was that number? FEE9. 0xFE9. That is 65,257, right? And just for reference, 2 to the 16, 65,536. So, if we look at our list of primes, we have to look at, get a larger list of primes. First 10,000. That goes past what we want. So if we come down here, bring SpeedCrunch back. So 6555535. Let's just look up 6527. 65257. 257. There are actually a bunch of primes we could have picked. I assumed that I just picked the largest prime less than power 2, which would have been 65521. Can I just do x 65521? That would have been FFF1, which maybe makes sense to use, actually. Huh, I wonder why we chose 257. Is the difference between those significant somehow? 65536 minus 279, which isn't anything of importance. At least it's not a prime. That makes that. It's a very curious choice there. If only I could go back and ask myself why I chose that number. Maybe it was the largest number in some list. So anyway, so what we do here, you'll notice DX just gets ignored completely. So we're just keeping the low 16 bits. And if we're going to design our own random number generator, we should probably come up with a way to verify that it's going to work. Actually, when it does divide here, so DX will be set here. No, it's going to be set here. And this is why it's worth drawing the whole thing. So let's just say rand equals seed times FE9. Seed equals rand. We're going to take that random number. Max rand is FFFF. So if we take that times that, that'll get us the number we want once we add 1 to it. Now theoretically, actually, if we actually rolled FFFF, which is a theoretical possibility, there's a 1 in 2 to the 16 chance that this apparently generates a number 1 too large. Never seen that happen, though. I mean, 2 to the 16, that's a lot of rolls. We could add something here that creates a histogram of the different rolls we could get and sees if we ever see a 7. So well, let's maybe try to just improve this guy a little bit. So if we're going to do a division anyway, and we're relying on this multiplication to generate us a value, right? AX should end up on the range 0 to FFFF. And keeping AX as seed makes sense. Maybe we should be multiplying by dx. So we take the high bits, which are not going to go from 0 to FFFF, and go from 0 to 1 less than this. Because if you take this and multiply it by 1, you're not going to get anything into those higher bits. And if you take this and multiply it by FFFF, you're going to get, well, let's look at it just to show you in Speed Crunch here. Just want to see the hex of it. 0x FFF times 0x F, was it EE9, right? Yep. So then our high byte would end up, would be FEE8, which is one shy of FEE9. So that's a more traditional random generation process. And then there's no reason not to use FFF1. Get us a little more range, and sure it'll go from 0 to FFF0. Yeah, let's do that. So here's what we're going to do. We are going to set up a max rand value. We'll use our defines up at the top here. Max rand equal, and we'll mark it in hex. So it's 0, FFF1, hex. And we can multiply that by max rand, and then we're going to divide by max rand, but we're going to do it after a, so we're going to have a move here. We're going to move into AX dx. Oops. Sorry, we're going to do that here. So this is going to change which is our random. So now our seed is going to equal, and this actually I forgot to put because we're only grabbing the low 16 bits of this. So it's seed, that's max rand. That's what this is fundamentally doing, but we're at the same time we're going to say our rand is going to equal the same thing, but we're going to take the high word of it, so that right shifted by 16 bits. Actually, we're going to put this comment here. Let's replace these max rands with max rand, being that we now. A 16-bit multiply into a 32-bit register that then we can divide out of. This is then, so the roll equals, and so this is your standard, and keep in mind this is an integer division, right? So this will sort of round it down when we do the division. And now we won't ever see the max. Now the one thing that might be nice to do is before we move AX into this word, kind of nice to add a little something to it just to get it right. So, but if you look at, pseudo random number generators, right? Usually they involve, there's many algorithms for them. But a sort of standard that was popular is a multiply and then an add. And you do that because if you multiply, so if your seed ends up even, your seed's going to always be even. And so because of that, your seed, which really determines what your output value can be, can only be half valid bit combinations. And the goal is you want it to be so that your seed, which is slowly cycling through, right? Because your seed is defined solely in terms of some constants in your seed. So you can never have more than 2 to the 16 in this design, different states that your random number generator is in. So at most, it will take 2 to the 16 before it repeats. 2 to the 16 random number generations. So if you were sitting there watching it, you could be like, you could look for the pattern, and if you collected all 2 to the 16, you would get it. The thing is, if we know that the seed's also always going to be even, we've now halved that number, which, because an even times anything is even. And an odd times anything is that other thing. So, and being that max rand is odd, it's going to keep the seed the same as what it was last time. So we could if we put a +1 in here, we at least know that it's possible to hit all the even and all the odd values. It's going to alternate between them, which is, its own problem for predictability. But this isn't we don't need this to be cryptographically secure. We only need it to be good enough that, someone who's rolling the dice doesn't feel like it's being unfair. We can run some tests with it after we make this mod. But we know that this is going to be better. Because now we know that AX, or our seed value, will always be, it'll alternate even odd, and it will hopefully cycle through all possible values. There's nothing now that strictly prevents it. And the reason that we make max rand a prime, it really just has to be not a power of 2. Your max rand and this number, if these two have a common divisor, that's gonna end up being a point, a repeat point, where it can repeat more often. So we want to just increment AX. AX will have this value, and then we're gonna put into the DX into AX, so that that's now our rand value, and then we'll multiply it by the die size we want, and then we can max rand that down. So this already should give us somewhat cleaner randoms. My guess is probably the reason that this was the way it was, because there's no way this didn't have an addition before here of some sort. So what this probably had before was, it was probably a multiply and then a add, and then I was probably like, the add doesn't seem to actually do anything for the scale we're looking at, so let's try this and see what happens. So we could actually take advantage of the fact that we can now see the actual random numbers it generates, right? Because if you don't set the die, it defaults to FFFF. It actually is going to not be able to generate that die because our limit is max rand. Fortunately, we can't see the seed value, but we can see it generates high values, low values. Actually, I wonder, can we see in the old value thing that it only generated... Because before we were actually printing AX. No, let's do that. Let's do something. Let's git stash that. First we'll get status. Git diff. Yeah, so all we did was did this max rand changes. So let's put that all back. It's like it was never done. As a matter of fact, if we come over here, it's going to ask us, do we want to reload, unless it already did it. Yeah, so Kate has a Git plugin, and it says, oh, you did a Git stash, you must want to go back. And it doesn't even ask you, do you want to reload? It just does it to you. So we're back to this FEE9 with no addition. And then it literally will make that seed value will be the random value. It's going to multiply it by FFFF, then divide it by FFFF, which will be a no-op, because it will now treat that as a value, so that's going to be what it writes. Let's see what happens when we run that. I'm going to do a clean all just because... What? Oh. Not a get clean all. Make a clean all. So now we've got our program running. So that's an even. Okay, so we know that, so we're literally looking at the seed value now. And we can see that it's never an odd value. What we could do is look at the seed value and then have this thing generate random numbers with a larger counter and see how long till it cycles around, right? It can just count until it sees that same seed value again. Because once it sees the same seed value, it has to cycle. We can just pick a seed value, say like, well, it might not ever get to a certain seed value. It also depends what your starting seed value is. But as you can see, it never generated a not even seed value. But now, so now let's restore our code. Git stash apply. There we go. And our code should be back now. And it's all back. Okay. So, and once again, it doesn't ask you, do you want to reload it? It says, oh, you brought it back from Git, you must want it. So let's do this. So up here, AX has the value we're going to write to the seed. So let's call writeNum up there. And we'll print our seed every time we go. So while the rest of this goes through using the DX value, the high bits, to generate a die roll value, we're going to also print the seed value. That way we can see sort of what's going on under the hood at the same time. Okay, so let's see. So now if I roll a, well, let's just hit a key. 56720 is our seed value. So, and then that other number is the rolling the, the 2 to the 16, die 2 to the 16. And I see the seed value. So let's roll die 4s, because that way it'll be easier, because what number will always be 1, 2, 3, or 4. Let's clear this, hit 1. So our seed value is even. Now when we run this again, we should see a seed value that's odd. We see a seed value that's odd. And a seed value that's even, then a seed value that's odd. Even, odd, even, odd. And that's because when you multiply by an odd number and then add an odd number, you end up changing whether you're even or odd. So that does mean this is predictable. Matter of fact, this is incredibly predictable, especially being that we're printing the seed value here. So if we grab speed crunch, let's actually move that to that screen. All right, we know what the calculation is going to be. So it's going to be 0x FFF1 times this number, 31787. We want to hex that though. And that gives us this number here. High order bits are die roll, low order bits are going to be used to generate the new seed. So let's calculate that out. So this plus 1 is going to be our new seed. So 0xb 97b plus 1. So we expect our next seed value to be 47484. And let's see if we can figure out our next roll. So it should be this. So 0x7c23 times 4 divided by our max value, which is 0xFFF1. All that plus 1. So this is saying we should see So this is almost 3, but it's still integer math, right? Integer division always rounds down, so we should see a 2. So we should see 47484 and 2 when we hit a 1 here. So let's hit a 1. 47484 and a 2. So it is predictable. Now, back calculating the seed from this number is actually fairly difficult. So if we weren't printing these out, I mean, you could investigate memory or something, but people aren't going to do that. We don't really have to worry about it. And if we just hit enter here, this is all die 4s, right? But as you can see, the seed value just alternates even odd, even odd. So theoretically now our time till repeat should be closer to 2 to the 16. I think because even if you put in 0, it's not going to end up going back to itself. So it's probably safe to assume this is going to loop all the way around. Now what we could do is write a program. We could have this program run until it gets to a certain seed value. Like, we could start at a seed of 0 and see how long till it gets back to a seed of 0. Yeah, you know what? Let's do that. If I do a clear, let's do 4 die 10. 1, 2, 3, 4, and then I total. Yeah, so it still calculates that total correctly because we're just printing out the seed. We're not actually changing the way it affects that. So let's see if we get what sort of values we see here. Back when I wrote this, my friends would say that this die roller would always roll low. So that's 10 die 20s. Let's see what the total's up to. Right, was it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. That's very high. I have a feeling I messed that up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, well that came up very high. But maybe that was just luck. Let's clear it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total. 142 again. There. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I do get the feeling that is rolling very, very high now. Which means I messed something up. Because what should it be? It should be... We'd expect 10.5, right? Obviously, we have to roll a lot more than this. So we'd expect 105 in 10 rolls. Let's see, do all of them roll high? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's spot on for the die 4. I mean, admittedly, this is a very small sample. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 42, so that's high. There we go. That's a low one on the D20. But we can let's do some. Let's test how long till this thing repeats. We expect it to be fairly balanced, and we'd like to see it repeat and take 2 to the 16 times to repeat. Now, we have two options. We could, I mean, we know that this, because we were able to do it by calculator, right? That means we could write a quick C program to test the algorithm. Or we could literally test it in line here. We could still put the prints in, because 2 to the 16 prints is a lot, but not a unacceptable amount. If we want to store the full table of all the possible die values, actually no, that's not a problem. So we could use the D100. We just need a spot with 100, allocate 100 locations. So there's a question. We probably don't have any real scroll back though in this thing, do we? So if I just hit, I don't know. Yeah, no, there's no way to scroll back. So we can't print all 100 values. We could do it with a different die, because we have like 20 lines here. But this should be 25 lines. 1, 2, 3, 5, 6, 7, 8, 9, 20. Yep, 25 lines. So we could take the 25 lines and say we're going to print, we use a die 20, see what the values we get for the 20 are, and then see what our total is. Sure, let's do that. So we're really gonna hack this thing up, but it'll let us test that this random number generator actually gives us nice results. What we're gonna do is we're gonna move 0 into the seed value when we come in here. So move. I don't even know if this is legal. Let's see. We might have to use a register in between there. Just want to make. Oh, it worked. Okay. So we'll move 0 into the seed word before we come in here. We're going to be looping this thing, so we're going to want to label up here. We'll just call it get next brand. Then when we come all the way down here, we want to check. The seed's going to be gone here, so let's just check here. So here, after we do this increment, we're going to be done. So we could, if that increment, right, so if you remember, increment does update the status flags. Increment, right, it updates the 0 flag. So what we're going to do, so we're going to start at 0. As we go through here, the seed's going to be not 0, it's going to be 1. But because it's going to be 0 times max rand, which will be 0, then we'll increment it by 1, so it'll be not 0. So if we jump 0 to, we're going to have something that's going to be called like print results. Otherwise, we're going to go through and do what we would normally do. When we get down here, though, we don't want to just write the number and the total. We want to increment. So first of all, we want to get a count. So let's put that count. We're not using CX anywhere in here. So I think we can use CX for this. So we're going to, up here, move into CX, 0. Yeah, so we'll just every time through here right away. We'll just increment CX, inc CX. We know it's not going to run 0 times. If it runs the full 216 times, it's going to print a 0 at the end. We'll just assume that if this went to 0, that if this is 0 still, then that means it went all the way around and back to 0. Deal with when we see it. Because we know that it's going to be more than 2, right? Because when it comes through as 1, when the seed's 1, it's going to be 1 times max rand, which is going to be FFF, whatever. And then it's going to make that be even, so it'll be FFF2. So that's one. So CX will keep our count of how many times we go to the loop, through the loop. So let's see if we can use AX to increment an array. So I want to check inc. Okay. Destination. It can be a memory location, and it can be, so it can at least be relative to BX. But I think this is the problem we had before, right? Where we're gonna have issues there. Do we care about BX at this point? We've divided by BX. Nah, we're gonna set BX before we use it again. And the only thing we use BX for in this whole thing is storing max rand so we can divide by it. So we need another symbol. I don't know, let's call it counts. DW. So it's going to be words. It's going to be just 20 words. And 21, because AX is already +1 here. You know, we can do it before we +1 it, though. We'll do that. We're rapidly eating up our memory available. We could always chop this menu out if we have to. So we're going to increment it before we increment AX. So this is going to end up being the roll without the last +1, and that's fine. Let's see, can we do counts? Sub, we gotta do it this way, right? Word counts. Oh yeah, you can do counts of AX like that. And I think because this is a word type, it'll know that we multiply AX by 2. Actually, let's see if it assembles. Nope. Let's see. Would it have worked if I'd used BX? No. Oh. It's because using that plus syntax. So maybe that's just what I need to do. If I do counts plus BX, will that work? Well, it got to a different spot before it errored, so I'm guessing it worked. Give me an error at the print results. Why didn't that give me an error before? Oh, because it went through. Found that one in the second pass. Now my concern is, so if I make this AX, so it has to be BX or base index, and then I need to know, is it going to know that because this is a word access, this has to be shifted by 1 first? We don't need this super efficient, so I'm not going to spend a huge amount of time. We're going to waste a little bit of space, but we're just going to move BX, AX, shift left, BX, 1. So that'll multiply it by 2, and then we're going to increment the word at counts plus that, which will get us to that. Does that assemble? Yep. Okay. So that means after we go through all of this, now we don't need this jump to label. We'll need that at the end. So then once we write the number to the screen, and we can comment out those screen writes if we decide that they're not helpful. But otherwise we're going to jump to get next rand. We started with our zeros. It'll run through. It'll hopefully have incremented them. This takes forever. We can. There's no need to print the seed anymore. Comment it out though. Maybe if we want it back, it's there that way. It would be nice to get some amount of feedback. So we'll go with the write num call here. And if it seems like it's taking forever, then we can come back and rerun it without it. We're gonna print the line that would normally come out after a total. So the dashes. So that's right here, this part of code. So we'll do that. After we print the dashes, we're going to print CX. So we're going to move into AX, CX, and then we're going to call write num. So there we go. So now that will print our total, which hopefully this will have looped all the way around and CX will be 0. And then what we'll do is we're going to loop through all these counts values and print them as we go. So what we're going to do is we're going to grab this chunk of code, but we're going to start by, we'll move 0 into CX, into CX, move 0, then we're going to move CX into BX, then we're going to shift that left one, then we're going to move the word there into AX so that we can write it. Then compare CX to 20. We got to increment CX first. There we go. We increment CX. Then we compare it to 20. Then we're going to jump, if it's not 0, back to print next count. Let's put that in the right spot here, which is this spot. And so this will print, this should print all 20 counts. Now I would kind of like to test this with less than the full run, but forget it. It should be pretty fast. Let's see what happens. We got an error. A legal instruction. I forgot a colon. Continue print results. I forgot to put print results down here. If you were following this along, you were probably like, what on earth is he doing with all this code down here? So when we get to the print results case, it's going to run down here and it's going to go through, print all the results. So we're going to print the dashes. We'll print the total times we went through this loop, and it will print all the totals of counts. So when we run this, though, it is important that we have to hit 7. If we hit anything other than 7, actually no, we can hit anything less than 7, we'll be okay as well, because it'll just use the lesser die values. So we're going to try it. We're going to hit 7 here, and hopefully, yep, well, we got a build, and here's all our zeros. We still haven't blown our memory budget, so we didn't have to spend any more time optimizing that than we did. Okay, so we just want to hit 6 to get die 20s. So this thing's chugging along. It's running at about 8 megahertz. Kind of curious. You can see it's almost sucking down all my CPU, and it's probably this thing. I'm surprised that this is that much of a multi-threaded load. Being that we can kind of see the numbers scroll by, it makes me think this is probably going to take quite a while. Yep, there it goes, and it's done. And so, yep, we got the 0, which means it went all the way around, so that's good. And we've got 327, and then some are 3276, some are 3277, and one of them is 3278. We got 1 extra in the lowest D20 value. I wonder, did we count the 0 one twice? No, we didn't. But that's pretty balanced. So let's see if we can get back our old random number generator and then run that again. The random number generator doesn't have any impact at all in this. We should be able to, so we're going to just take out the increment. Without that increment, though, we need to have a test, I guess. Compare AX with 0. We were not multiplying by max rand before. We were multiplying by 0 FEE9. Yes, FEE9. And then we weren't dividing by max rand. We were dividing by... And we weren't doing this move to dx. So now we have the old algorithm, right? So we multiply by this, and we just use what's in AX. So we use the seed value. You know, it's a couple instructions less, and I'm sure that's what I was thinking when I wrote this, but really not helpful. Make it first. Well, it built. Make run. So then we hit 6 to get d20s. It ran once and generated no random numbers. So what did we do wrong? Well, obviously, if it's 0, if you put in 0, you're going to get 0. Because all you're doing is multiplying. So, I mean, that's already a huge problem with this algorithm, right? But let's assume we got an odd number to start. Okay, I must have done something else wrong. Because it definitely wasn't that bad. Oh, whoops. I put that in the wrong spot. That should be 0. That should be 1. There we go. Now it's generating some numbers. Let's see what we get. Okay, so it's fairly balanced, right? You got 410 or 409, but the sequence is only 8,192. So that means that, I mean, as you saw, there are values that are just going to cause it to lock up. The fact that 0 caused it to lock up is already, you know, a sign of how unreliable this thing could be. And I was probably using it before, and sometimes I'd run it and I'd be like, huh, it seems to be generating the same values. It was 8,000. Let's try giving it an even number to start that's not 0. Let's start at 2 and go until it gets back to 2. So we know 2 is not anywhere in that other list, but we know that one didn't even hit all the odd numbers. So this one generated about 4,000 values. So you can see that it's not as good as something that's only slightly more math, but hits all those values. So let's put this all back and run that one more time. Bring back this move. Let's go back to max rand. It was nice, though, to see that it at least was giving you a fairly even distribution. So the numbers, though they were shorter sequences of random numbers, it wasn't weighted in any direction. Now, that's obviously not completely true for all the sequences it can generate, because 0 is a possible sequence, and 0 is going to give you a random number of your minimum value. Let's run that one more time. Make sure that... Oh, let's go back to... I mean, it doesn't really matter what value we even start on. Except for I'm comparing to 0 here. I'll have to put the compare back in. Let's do it. Rather than incrementing, we'll just do it. We'll add an extra compare. Now let's give it the old 6. So now, even though we started at a different spot, because we know this one goes through all the values, it should still go through all the values. It's just going to start wherever 2 was in the series and go all the way around through all of them back to 2. Chugging along. Yeah, I guess we had enough time before to look at htop. Oh, there it finished. Just waiting for me to look away. So here we see the same, same exact sequence, right? Because it's a deterministic process. So you're going to see the same exact result regardless of what value we start at. So this guy does give you one more 1 and 1 less 20 than the sort of average it gives, which is interesting. But that's probably just, that's related to the fact that we're generating random numbers on that sequence from 0 to FFF1. And now there's not a direct tie between the two. But it's pretty balanced. So let's actually reset. And so now we can go through all the values again, but let's see how balanced is this on D12s. It's going to take about the same time. It should have to go through the same 2 to the 16 values. Yeah, sorry, everything beyond 12 is 0. So here you see we got a nice even balance. Again, it favored the low value, but, only by 1 in thousands of rolls. That's a pretty good sequence. Let's reset, and let's do Pt6s. So the reason we have to reset is because we're not actually clearing that array. We're just relying on it to be loaded with zeros, right? We load it with zeros, but we don't ever actually clear it. So if we just hit another number, then it would just add the totals onto the totals from before, and that's not helpful. So, but it's not that hard to hit reset. It's, it has to load the 512 byte bootloader. That does not take long. And you can see, again, it went through all the values, because again, there's no reason the seed value would ever change, or the total seed values would ever change, because it went all the way around, going all the way around every time. You can see, once again, it favored low. So that probably is indicative of the way this thing generates. But for anything even reasonably small, you're not going to see a significant difference anywhere in here. Now, I could roll D100, but that would cause it to start to modify, right? So roll die 100. Do we want to see this thing go really bad? I think we do want to see it go really bad, right? So here are the first 20 values through here, right? But then right after that is that write function for the writing a number. So as soon as we roll over 20, this program's going to start to get bad. So I vote we do it, though, because why not? I like me a little fun. I think if I hit clear, yep, it brought me back the menu, but it still didn't clear that array. So let's roll us, hit a 7, and get some die 100s. Yeah, we got 100 almost immediately. The program stopped being able to print numbers, which isn't that surprising, and it's probably run off into the weeds. I mean, 84. Let's stop this thing. So 84 was the last one it generated. 84 would be... Yeah, so I mean, it would have been poking all over memory. So that would obviously is bad. So that would be bad programming, because you're not protecting your code from user memory accesses. We've now shown that this is a much better random number generator. So we're going to use this one instead of the one that was originally there. Actually, let's do this. Let's save this in Git so that it's here if I ever want it again. I could, I suppose, put it on a branch, but I'm not going to do that. It'll just be here in my history. And I can go back and look at it and admire its weirdness later, if I ever care. So, test code to loop through all possible seeds. Verified that all seeds are hit and output is fairly balanced with new random number generator. Actually, you know what? Let's try one other thing. So what if instead, let's just change the value of max rand. What if we kept the FEE9 that it was, but use this algorithm instead? So I mean, we could literally make this number anything, and this is going to generate us legal dice values because of the way it works. Now it's going to go through a different sequence though now, but it should still eventually go through all of them. This is still a prime number, so it should have to go through all of them before it gets back to where it started. We're still adding the 1, so we hit both the even and odd ones. This should take about the same amount of time. It should have to calculate the same number of values. We'll see if it, gives us a good balance. Now the thing is, we're going to get less of a spread in that DX register, though, that we use to feed in, right? Because now instead of it being between 0 and FFF1, now it's going to be between 0 and FEE9. But you actually look at this, so this one, we still favors low, but not because low is high, but because high is low. And I mean, we could sit here until we get a number that, gives us maybe a nicer distribution for what we want. But I think it's an unreasonable amount of effort. But this shows that, even if we chose a different prime, it needs to be ideally a prime, and it needs to be big enough that these dice value, like 20, ends up dividing it into it a fairly large number of times. So what if we pick 21 is prime? Probably going to give us a horrible result, right? No, 21 isn't prime. 21 is 3 times 7. Come on. Get on the trolley. I do have that list of primes. I mean, I could choose 13. Gonna be a problem. We could do 13 and 12. Roll d12s. The prime of 13. That would probably look like just bad. Right, so we could pick one of these. Like, here, 401. That's like 20 squared plus 1. Seems like a nice spot to be. So this is still prime. So now it can only generate numbers between 0 and 400. It has to use that to get the dice value. We'll see how that goes. No, actually, run just a make. Okay, built clean. Make and run. Continue. And let's roll that die 20. The seed value, which is the low order part, is still going to have to go through all the possible values to get back. I wonder if this gives us more of like long runs of values. It's hard to say. I mean, looking at the screen as it flies by, it looks like we have about as many two-digit numbers as one-digit numbers. Okay, so it just finished. It went all the way around, but see, it really favored that low value. And that's probably because of the way... because I think we're fundamentally doing like an indirect modulo here, and so this is probably where that wrap comes in. But this really favors that low value. So what we could do, though, is we could go the other way with FFFF. So now what we're saying is, so this is the largest odd number, but this isn't a prime number. So it's more likely we're going to have cycle issues, but let's see. And who knows, maybe FFFF will work beautifully. I don't think it will, but I don't know that it won't. I mean, it's still relatively prime. So let's give that 6. And it went once. Did we end up back at 0 from... That doesn't make sense. How can we have a total of 3 values in here if it only went once? 0... Oh, no, sorry, it went twice. Okay, sorry, it's not above the line, it's below the line. So it went twice, and both times it rolled a 1. And then it stopped. That was worse than I thought it would be. It wasn't good, but that was worse than I thought it would be. But I guess that makes sense, right? Because if you... So it went from what? Where did we go from 2 to 2? So the first time through it was 2. So 2 times that's going to put 2 up in dx. Because basically we're almost shifting the seed to the left 16 bits, but then we're just barely not. But yeah, so that obviously was bad. But if we use FFF1, we get a pretty good distribution. It just all in all works nicely. So anyway, let's put this back. And let's pull out some of this stuff. So we don't need get next rand and all this stuff anymore. We don't need actually this anymore either. We don't have to compare it to 0 and print the results, or compare it. We're still doing that move. We still need to multiply by the dice. That's all still the same. So that's our random algorithm. And this guy here is our increment our count, which we don't need to do that anymore. We don't need to increment CX because we're not using that as our counter anymore. So real quick to go through here, we take our max rand value and we multiply that by our seed. Then we add 1 to it, which is this. And then we're going to take just the low 16 bits of that, and that's going to be our new seed. Then we take the high 16 bits of that, and that's going to be our random number, which we then take and multiply by the die value that we're rolling. We divide that by our maximum random value. And just keep in mind this is going to be a 32-bit multiplication, or a 32-bit result. And then we're going to divide that max rand into that 32-bit value, which will get us back to a number on the range from 0 to the dice size, add 1, and we're going to actually put that here. And then that gives us our roll here. And then we can add that roll value to our total. And we write the number, because that's the important part. And then we're not going to jump to get next rand anymore. And we don't really need all this print results stuff. So really, I think we're just about done here. So we're not going to print the next count. We're not going to print the results. After we write the number, we're done. We can just go back to label A, which is a terrible name for the first label that was what was probably the first label in this program. It should be called something like read-a-car, but that's fine. We can fix that later. Oh, we don't need these counts anymore either. We're just wasting memory. Okay, let's save that. Rebuild. So that rebuilds. And our program's back to that like 130 sort of area it was before. And now we make it run. Now, if we roll, let's try 10D100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total. Little low. Little low again. There we go. High one. That one had a 1 in it and got high. But I had a lot of, I had a 99 and a 97. A good roll. So yeah, I mean, I would expect, merely 10 rolls to see something in the, 400 to 600s. Right? Like, and if you see a 600, like we saw a 600, 600's obviously further from the 50.5 we would expect than the than 489 is, right? That's pretty good. And I think that so let's do a diff and check our. So now we're gonna have the diff of us removing all the test code, but we can see. Yep, we removed all the test code. But we also have our new random number algorithm in there. So, git init -a removed test code, new random number generator integrated. So, I think that's a good change for now. The next change we make will probably be the last change we make, which will be basically refactoring this part. So we've rewritten we wrote all this from this new. Oh, I did want to compare this right line to the one that was in io.asm, which may have come with the A86 assembler, or I may have written. Oh, no, sorry, io.asm would be the right num, right? We can compare this right num with that one. Maybe we'll do that next time. And then after that, then we'll redo this. And maybe we'll just do both of those at once. So anyway, good luck out there, and happy hacking.